chapter 2. I ended in dipole-dipole interactions. So London dispersion forces, they are one of the van der Waals forces. A temporary dipole moment in a molecule can induce a temporary dipole moment in a nearby molecule. An attractive dipole-dipole interaction results for a fraction of a second. And the main force, these are main forces in nonpolar molecules, and larger atoms are more polarizable. So if we look at dispersion forces or London dispersion forces, they're random temporary dipoles when they're separated. However, when they're in contact, you have temporary dipoles that correlate to one another, where you have plus minus being interacting with one another. So if we look at properties such as boiling point, there is an effect of branching on the boiling point. In the case of pentane, isopentane and neopentane, you're seeing branching occurring as you're going from left to right, and the boiling point, it seems to decrease as you increase the branching. So the long chain isomers of pentane has the greatest surface area, and as a result leads to the highest boiling point. As the amount of chain branching increases, the molecule becomes more spherical, and its surface area decreases. The most highly branched isomer, or neopentane, has the smallest surface area and the lowest boiling point. Hydrogen bonding is defined as strong dipole-dipole interactions. Organic molecules must have NH or OH to be able to form a hydrogen bond. If they don't, they can't. The hydrogen from one molecule is strongly attracted to a lone pair of electrons on the other oxygen of another molecule. And OH is more polar than H, so alcohols have stronger hydrogen bonding in general. So here are examples of hydrogen bonds. This is methanol, where the lone pairs are then hydrogen bonding with the hydrogen of the methanol itself. So here's that. Here's another example of methylamine, in which again the lone pairs are hydrogen bonding from the nitrogen, this time instead of an oxygen, with the hydrogen, and it requires that the molecules have a dipole. Boiling points and intermolecular forces. So if we look at ethanol and dimethyl ether versus ethanol and ethylamine, the hydrogen bonding increases. As that increases, it also increases the boiling point of the molecule. So here's ethanol, its boiling point is higher than this because it has that H for hydrogen bonding. OH is more polar than NH in the case of ethylamine versus ethanol. So alcohols have stronger hydrogen bonding and therefore higher boiling points than, for example, ethylamine. So let's look at another problem, problem 4. Rank the following compounds in the order of increasing boiling points. Explain the reasons for your chosen order. So here are the molecules shown here that you want to rank. Here's your solution. To predict the relative boiling points, we should look for differences in 1. Hydrogen bonding, 2. Molecular weight and surface area, and 3. Dipole moments. Except for neopentane, these compounds have similar molecular weights. Neopentane is the lightest, and it is compact spherical structure that minimizes van der Waals attraction. Neopentane is therefore the lowest boiling compound. Neither N-hexane or 2,3-methyl butane is hydrogen bonded, so they will be next higher in the boiling points. Because 2,3-dimethylbutane is more highly branched than N-hexane, 2,3-dimethylbutane will have a lower boiling point than N-hexane. The two remaining compounds are both hydrogen bonded. Pentane 1-ol has more area for van der Waals forces. Therefore, pentane 1-ol should be the highest boiling compound. So we predict the following order: neopentane being the lowest boiling point to pentanol being the highest boiling points. And the actual boiling points are given below. So there are also polarity effects on solubility. Like dissolves like. Polar solutes dissolve in polar solvents. This is important. Nonpolar solutes dissolve in nonpolar solvents. Molecules with similar intermolecular forces will mix freely. So if you take polar and nonpolar, they will not necessarily mix. So polar solute and polar solvent. A polar solute dissolves in a polar solvent. Hydration releases energy and entropy increases. And so if you see an ionic crystal lattice in water, ionic crystal lattice are usually found in salts, for example, then the water will solubilize, in which it will line up with the positive charges in one way and line up with the negative charges in the other way. This hydrates the ions, allowing for salt, for example, crystals to dissolve. Here's a polar solute in a nonpolar solvent. Again, this is an ionic crystal as in a salt. Here's a nonpolar solvent. These molecules, because they're nonpolar, they can't wrap around any of the ions and break apart the intermolecular interaction, so you're not going to see dissolution of the salt. If you have a nonpolar solute in a nonpolar solvent, these are greasy nonpolar solids. They have weak intermolecular forces. These are nonpolar solvents, so they can actually come in between the stacks, dissolving the weak the nonpolar solid shown here. And then if you have a nonpolar solute with a polar solvent shown here, again, here's a nonpolar solvent, here's a polar solvent. These will form hydrogen bonds with one another, not really interacting with the nonpolar solvent, so you won't have it dissolve in the water. Classes of compounds. Classifications are based on functional groups. There are three broad classes. Hydrocarbons. These carbons are composed of carbon, only hydrogen, and carbon. Compounds containing oxygen and compounds containing nitrogen. Hydrocarbons, under hydrocarbons there are different types of molecules, and we'll be talking about these in the next chapter as well as naming them. Alkanes, they're single bonds between carbons. All carbons are sp3. Cycloalkanes, again, sp3 carbons, but these are now formed in a ring structure. Alkenes are double bonded structures. They're present in molecules where you have sp2 carbons. Cycloalkenes, they're rings with double bonds in them. Alkynes are triple bonds with sp carbons, and aromatics are essentially carbons containing structures with a benzene ring, which are essentially have double bonds between every other bond. Compounds containing alcohols. These are alcohols, ethers, aldehydes, and carboxylic acids. You should know all these names, starting with all hydrocarbons and oxygen-bearing as well as nitrogen-bearing compounds, which I'll talk about in the last slide. In the case of alcohols contains a hydroxyl group as the main functional group. Ethers contain two alkyl groups bonded to an oxygen. Aldehydes and ketones contain carbonyl groups, or C double bond O, and carboxylic acid contains C double bond OOH, which is shown here. Compounds containing nitrogens, they're amines. Amines are alkylated derivatives of ammonia. Amides are carboxylic acid derivatives with nitrogen attached to the carbonyl group. And then nitriles contains cyano groups. So this concludes chapter 2. And so again, you should be doing all the problems prior to class, because we'll be going through problems within class. And also you should be doing problems and getting a lot of practice with this.